We saw in the case of free scalar fields that we could write the path integral in the form of a Gaussian path integral, which we can then solve exactly. So we are going to do the same now in the case of our free vector fields. And in particular, we will focus on obtaining the propagator, the free propagator for vector fields, which will tell us how efficiently a disturbance of the field propagates. So we see that what we have to do in order to get the propagator is to find this function, which we wrote a in the case of scalar fields, in such a way that the space-time integral of the Lagrangian can be written of a double space-time integral of the field, the function a, and then another field. One important difference in the case of vector field is that now the field and the source both carry a Lorentz index. So what we try to do is to write our path integrals in the following form. So what I wrote as a in the case of a scalar field, I now wrote as b because I use a for the vector field itself. And of course, because the action is a scalar, all the Lorentz indices have to be contracted. And because we have one Lorentz index per vector field, and we have two fields, we need two Lorentz indices for the function b. We already got an expression for the action for a vector field in which we had the vector field times a function times another vector field. And we also determined that alpha is equal to +1/2. We will do a bit of massaging of this expression, like the introduction of a metric in the mass term. And we introduce a delta function with another integral over y. We recover the desired form. This gives us our expression for b mu nu. And we then recognize a Gaussian path integral, which we are now able to solve. The propagator now has two Lorentz indices, and it is obtained as the inverse of b mu nu. If b and d did not carry any Lorentz indices, this expression will be simply given as what we had before in the case of the scalar propagator. Now that b and d have two Lorentz indices, they are ranked 2 Lorentz tensor, we can treat their multiplication as a matrix product with matrix elements given by the two Lorentz indices. And in that case, the matrix element for the identity is just the Kronecker delta. We now replace b by its expression. What makes things complicated is all these derivatives. And the trick is usually to go into a momentum space by a Fourier transform, which makes usually the equation simpler, because it will transform all the derivatives by momenta. So we already did some calculations with Fourier transform in some detail, and what we realize is that when we can do a quick Fourier transform simply by replacing derivatives by I times the momentum, del squared by minus k squared, and the Fourier transform of the delta function is just 1. That's the expression which our propagator in momentum space must obey, and it's indeed much simpler because we don't have derivatives anymore. So I'll give you the solution, and we will check that this is indeed a solution to this equation. As in the scalar case, I introduced an I epsilon term to avoid division by 0. We now substitute in the above expression in order to check that this is indeed a solution. The product of the two metric g mu lambda with g lambda nu gives a Kronecker delta delta mu nu. Then the second term here is obtained by applying the metric on k lambda to raise its index. So that gives us a k mu. Similarly, the third term is obtained by lowering this index with the metric. And finally, by multiplying this term with this one, we recognize we have a k lambda with an upper index and k lambda with a lower index. That gives us a k squared. In the first term, I have a division of k squared minus m squared by itself, which is well defined. It gives 1 when I take epsilon goes to 0. So that's the right-hand side of the equation I want to show. Therefore, what I need to show now is that this term is just 0. Indeed, I have minus k squared times k mu divided by m squared, and I have exactly the same term at the end with an opposite sign, so they both cancel. That leaves me with m squared divided by m squared, which just cancel, and I have k mu minus k mu, which also cancel. I have then verified the expression for the free propagator of a massive vector field. Notice that we need to have mass not equal to 0 because we are dividing by the mass in the numerator. However, it turns out that for physical processes like scattering between particles with the exchange of a photon, or for the interaction between sources, as we will do in the next video, this term does not contribute. Also, to get the photon propagator, we will need to account for gauge invariance coming from this additional degree of freedom we have when the mass is set to 0. We can choose the gauge in such a way that the photon propagator end up being So this is the expression for the photon propagator in a specific chase of gauge called the Feynman-Tofte gauge. We are not going to show this expression. We are only going to show that in some example of physical processes, like the Coulomb interaction or Feynman diagrams later, this term does not contribute, and we can safely take the mass to 0 and therefore use this propagator for the photon.